last week we covered several algebraic derivative rules, including power rule, constant rule, product rule, quotient rule, and so on. This week we're going to cover 16 more derivative rules, and these are all on a document, on Canvas called Derivative Rules. It's 4 pages. Page 1 has the 6 rules from last week. Page 2 has 4 rules for the derivative of exponential functions and logarithm functions. Page 3 has the derivatives of the 6 trig functions. Page 4 has the derivative of the inverse trig functions. So I'm not going to write all those down, but you do have to know all 16 of those. As for proving them, I'll show you the proof for the derivative of sine. The other 5 trig, well, the proof for cosine is similar, and then the proof for the other 4 just uses quotient rule. For the exponentials, I'm not going to show you a proof of the exponential. I may talk about it in a workshop, but the logarithm and general exponentials follow from that. And for the inverse trig, I'll talk about a proof of those next week, in week 7, when we have another result. But for now, I'm just going to show you a proof for the derivative of sine x. So proof that the derivative of sine x, according to that page, derivative of sine x is cosine x. So how can we show that? Well, let's use our definition of the derivative. So maybe I should say f of x equals sine x, f prime has cosine x. Well, whatever, I'm just going to call that f. F prime of x, limit as h goes to 0 of f of x plus h, sine of x plus h minus f of x, so minus sine x, all over h. Well, we can split this sine of x plus h up using, that probably won't fit there, using a trig identity, which we haven't discussed yet, which you don't need to know. The only time it'll show up is here, and I'm not going to ask a proof of this. But the sine of x plus h is sine of x cosine of h plus sine of h cosine of x. So it's sine of the first variable, cosine of the second, plus the opposite, sine of the second, cosine of the first. And then we'll leave the rest alone. Now, what we're going to do, this marker's running out of ink. I thought this was a new marker. Now, what we're going to do is rearrange this fraction. So, what are we going to do? I'm going to take this first piece of the numerator and this negative sine of x and split the fraction using those, and also split the other. So, what do I mean? I'm going to take sine of x, cosine of h, and negative sine x, and put them all over h, and then I'm going to take this piece. So plus limit h approaches 0 of, what is it, sine of h, cosine of x, all over h. So I took this piece and split that limit there, split the fraction there, and then split the limit, and then I did the same with this piece. So what can we do? Well, need more board space. I'm going to go up here, I guess. Equals. What can we do here? Well, first, I'm going to factor out a sine of x, because we can do that. It's a limit as h approaches 0, so sine of x doesn't change as h approaches 0. Sine of x, as far as h is concerned, is a constant, so I'm just going to take sine of x out, times the limit as h approaches 0 of, what are we left with? Cosine of h minus 1 over h. And what do we have here? Well, we can do the same type of thing. I'm going to take cosine x out, and we're left with limit as h approaches 0, sine h over h. Well, let's look here first. if we look at this, we have limit as h approaches 0, sine h over h. We know that limit. We used squeeze theorem to show that that limit is 1. So, on this piece, we have cosine of x times 1. This limit right here we have not seen, but I will tell you and I will show you in a moment that this limit is 0. So if this limit is 0, which I'll show in a moment, then this equals sine x times 0. Sine x times 0 plus cosine x. This limit is 1. Sine x over x as x goes to 0 is 1, so sine h over h as h goes to 0 is 1. And then if you simplify these, they just simplify to cosine of x. So all that's left to show is that that limit is 0. How can we show that? Well, I'll show you over here how we can show that. So that proof is technically not complete without this, so let's complete the proof. To show limit h approaches 0, cosine h minus 1 over h equals 0. Well, what we're going to do is take this limit. I need a different marker. That must be a used marker. So this one looks new. Limit h approaches 0, cosine h minus 1 over h. Well, what we're going to do here is multiply by a convenient 1. There is a convenient 1 we can multiply by. Cosine h plus 1 over itself. Now, why can we do that? Well, we do that because of the trig identity, sine squared plus cosine squared equals 1. Where does that show up? Well, denominator we'll leave alone. What do we have in the numerator? Well, we have cosine squared of h minus 1 from the difference of squares. But remember, sine squared plus cosine squared equals 1. So what's cosine squared minus 1? Well, cosine squared, so cosine squared minus 1, bring the negative 1 over, equals negative sine squared. Now, how is that going to matter? Well, let's see. Cosine squared minus 1 is negative sine squared. So this numerator is negative sine squared of h. And the denominator we haven't done anything with. Well, what can we do with this? Well, look at this again. We have a sine h over h. I'll go down here for that. Equals limit h approaches 0. Let's just rearrange that so sine h over h is thrown in front of our faces. So if we just write that numerator as sine h times negative sine h and leave the denominator alone, well, right here we have sine h over h. So we can actually split this fraction into those two pieces. As h approaches 0, sine h over h approaches 1. So this equals the limit as h approaches 0 of just the remaining piece. Negative sine h over cosine h plus 1. And now, how can we do this limit? Well, we can do a direct substitution, and we get that that limit is 0. So now we have shown the derivative of sine x is cosine x, because we showed that that limit in there is 0. And again, that won't be tested, but it is nice to see that argument. But for now, let's practice using the remaining derivative rules. So we'll do, I don't know, probably like 8 or 9 examples of these, And you're definitely advised to practice them using a worksheet, textbook, whatever you want to practice them. They're all very important. Well, maybe a couple of them aren't that important. I've never asked inverse cosecant or inverse secant. But they could all show up, so let's see how we could do them. Well, the first one, we have f of x is x cubed sine x. So the first observation here is that we have a product. So we have an x cubed times sine x. So we're going to need the product rule. What does the product rule say? Well, it says the derivative is given by the derivative of the first, which is 3x squared, leave the second alone, plus the first times the derivative of the second. So the first rule on page 3 of that document says the derivative of sine x is cosine x. Or that argument we just went through shows that as well. So for the first one, we had a product rule. Derivative of the first, second, plus first, derivative of the second. And you do not have to simplify any of these. Simplifying them will just get in the way. How about this next one? Well, we have a quotient now, so we need the quotient rule. How do you take a derivative of a quotient? Well, what is it? Bottom, derivative top, minus top, derivative bottom, over bottom squared. So let's just write them. Bottom is tangent x. What's the derivative of the top? Well, it's a polynomial, so we can just do it one piece at a time. 2x plus 2 plus 0. Minus the top times derivative of the bottom. Derivative of the bottom, tangent x. Well, we didn't prove that. If you wanted to prove the derivative of tangent x, you could use the quotient rule because it's sine over cosine. I'll probably put that on the worksheet, actually. Or you could look at the list of rules. Derivative of tangent is secant squared of x. And we haven't finished our derivative yet. All over bottom squared. So all over tangent squared of x. And again, you do not have to simplify. How about part C? F of x is x log of x with base 9. Well, again, we have a product, so we need to use the product rule. So we have product. Those two things. So what do we get? Well, derivative of x is 1. So derivative of x is 1 times the second log of x with base 9 plus the first, which is x. What's the derivative of log of x with base 9? Well, that's given on page 2. It is the probably the fourth one on page 2. Derivative of log of x with base b is 1 over x natural log b. That says natural log. 1 over x natural log 9 here. So we have 1 over x natural log 9. So we have derivative of the first, which is 1 times the second, plus the first times derivative of the second. With this one, so if you left it like that, that's full credit. And I don't like seeing that x over dx there, so I'm just going to simplify that. So during workshop, I may mention something about the proofs of the logarithm rules, depending on what kind of time we have. But for now, I'm not too interested in it. Part D. Well, what do we have here? Cosecant x over e to the x plus x. Well, how would we do that? Well, again, it's a quotient, so we should use the quotient rule. The derivative of a quotient is what? Bottom. Derivative of the top. What's the derivative of the top? Well, the derivative of cosecant x, given by rule 4 on page 3 of that document. Derivative of cosecant x is negative cosecant x cotangent x. So I could write it negative cosecant x cotangent x. I'm just going to throw the negative out in front. So we have bottom, which is e to the x plus x. Derivative of the top, negative cosecant x cotangent x, minus the top, cosecant x, derivative of the bottom. Well, derivative of e to the x is itself. It's actually set up so that the derivative of e to the x is itself. It's one of the reasons it's so important. And again, I may mention something about that on the worksheet, but I probably should. So what do we have? We have bottom, derivative top minus top, derivative bottom, derivative of e to the x is itself. First rule on page 2, derivative of x is 1. So we get e to the x plus 1. And this is not done. We need to put this all over bottom squared. So we have bottom, derivative top, minus top, derivative bottom, all over bottom squared. Now how about part E? Well, right here, tangent to the negative 1 is not 1 over tangent. Tangent to the negative 1 is the inverse tangent function. Here we have e to the x. We have e to the x times the inverse tangent of x. E to the x times inverse tangent x. Well, that's another product rule. So the derivative, e to the x inverse tangent x, well, the derivative of e to the x is itself. And then leave the second thing alone. So e to the x inverse tangent x plus, so we did derivative of the first times the second, now we need the first. E to the x, derivative of inverse tangent. For the inverse trig functions, I will mention the proof of at least one of them, and the others are similar. I will mention that in week 7, toward the end of week 7. But for now, we just have that chart. I'm giving you the chart now to get used to all the rules. It's on the last page of the chart. The third one down on the last page says derivative of inverse tangent x is 1 over 1 plus x squared. So we have the derivative of the first times the second plus the first times derivative of the second. You may want to rewrite this. Well, you don't have to, but I'm going to. Like that. And notice here, the derivative of e to the x is itself, so it does show up like that twice in the product rule, in using the product rule. Let's do a couple more of these. Let's see, we didn't do a natural log, we didn't do a general exponential. Let's do another trig or something too. Let's see, where's my list? How about f? I don't want that one to be f. F. Seven to the x inverse sine of x. G. Let's do this one will take up a lot of room. This should fit on the board. 4x squared minus 7x cubed times cosine x minus secant x. And let's do one more after this h. So we did general exponential. We didn't do a natural log, so let's do one with a natural log. Let's see, we did cosine, secant. Let's do inverse cotangent. And let's throw it in a product. Now let's throw it in a quotient. Yeah, let's throw it in a quotient. And again, this is not cotangent x to the negative 1. It's the inverse cotangent. Log x over inverse cotangent of x. And then we'll make a couple more observations after these. So for part G, Well, actually, for parts G, or part F and G, we have some more product rules. So let's do part F first, because that's first. Well, we have a product rule of 7 to the x times the inverse sine of x. Well, what's the derivative of 7 to the x? Page 2, rule probably 3, says the derivative of b to the x is b to the x log b. The exponential is set up so that that would simplify to 1. But the general exponential says the derivative of b to the x is itself times the natural log of the base. So here, b is 7, so we have 7 to the x, natural log of 7 is the derivative of the first. Leave the second alone, sine inverse, plus, leave the first alone. Derivative of the second, well, on page, which page? Page 4, we have the derivative of the inverse trig functions. The first one there says derivative of the inverse sine is 1 over 1 plus, or 1 over 1 minus x squared under square root. So I'm just going to write that like that. So it's derivative of the first times the second plus the first times 1 over root 1 minus x squared. And I'll just write that last piece as one fraction, which you don't have to do, but I do. Next, I'm going to answer part G down here and hope it fits across this board. Next, for part G, you could distribute this out. It would turn into 4 product rules. I'm not going to distribute that out. But now we'll just use one product rule, because we have this thing times this other thing. So the derivative of the first is 8x minus 21x squared times the second, cosine x minus secant x, plus the first, times derivative of the second. What's the derivative of the second? Well, we have two things added together. We do them one at a time. Derivative of cosine x is negative sine x, rule 2, on that third page of the derivative rules. If you want to prove that, it is similar to the proof for sine. So we have negative sine x minus derivative of secant. What's the derivative of secant? Well, you could use the quotient rule to prove this. The derivative of secant, rule 5 on page 3, is secant tangent. Secant x tangent x. And then that negative sign is still there. So here we have the derivative of the first times the second, plus the first times derivative of the second. So now let's do this last one before making some additional observations. So this last one we have a quotient, so we'll use the quotient rule. This is what, h f prime x, so we have the quotient rule. Derivative quotient is bottom, derivative top, minus top, derivative bottom over bottom squared. So bottom is cotangent inverse. Derivative of the top, well, rule 2 on page 2 of the derivative document says derivative of natural log x is 1 over x. I'm just going to write that like this. You could write it times 1 over x, like that if you want. I'm just going to write it as the one fraction. It's less writing. So we have bottom, derivative top, minus top, derivative of the bottom. What's the derivative of cotangent inverse? Well, the last rule on page 4 says the derivative of cotangent inverse is negative 1 over 1 plus x squared. So we have bottom, derivative top, minus top, times that, so minus top times that. I'm going to pull out the negative in front and make that a positive. Write that as one fraction, all over bottom squared. not cotangent to the negative 2x, the inverse cotangent squared. So we have bottom derivative top minus top derivative bottom over bottom squared. Let's do two more things. Not two more computations, let's make two more observations. Well, one observation, one computation. Let's start with the computation. Find an equation, example. Find an equation for the line tangent to what? To 3x squared cosine x at x equals pi. And then we'll do this last one. So find an equation for the line tangent to this function. Well, for a tangent line, we need a point and we need a slope. We need a point and we need a slope. Well, the point is when x equals pi. So we have x equals pi and we need a y value. Well, the y value is 3 pi squared times cosine pi. What's cosine of pi? Cosine of pi is the x value. The x value there is negative 1. So f of pi is 3 pi squared times negative 1, which is negative 3 pi squared. And now we need a slope. Well, the slope is the derivative evaluated at pi. I don't see a derivative for this function anywhere. So let's find the derivative. Well, f prime of x is given by what? Well, here we have, notice, a product. So you can use the product rule. The derivative of 3x squared is 6x plus, what's the derivative of cosine? Derivative of cosine is negative sine. And I'm going to put that negative out in front. So we have derivative of 3x squared is 6x, derivative of cosine is negative sine. So f prime at pi is what? Well, it's 6 pi cosine pi minus 3 pi squared sine of pi. I left that there for a reason. Cosine of pi is negative 1. So this piece is negative 6 pi. Sine of pi is the y value. Sine of pi is 0. So negative 6 pi minus 0 simplifies to negative 6 pi. So we have our point is pi and negative 3 pi squared. Our slope is negative 6 pi. So the equation for the line is y plus 3 pi squared equals negative 6 pi times x minus pi. So we needed a point and we needed a slope. Let's make one more observation. So everything we've done so far, we've just taken one derivative. Well, we could go on from that. We could take the derivative of the derivative. And then you could keep going on. You could take the derivative of the derivative of the derivative, and so on. And we call these higher order derivatives. Higher order derivatives. So we've taken first derivatives. So I'll just say the derivative of the derivative is called the second derivative. and so on. Meaning the derivative of the derivative of the derivative is the third derivative, and you can keep going for any number, well, for any whole number after that. The notation, so we'll probably not really see anything with third, fourth derivatives. Maybe one or two questions throughout the semester. The notation, we will see the second derivative a few times. So we will establish a notation for that. The notation for the second derivative is, so we had a bunch of different notations for the first derivative. So for the second derivative, one way of writing it is f prime prime of x. It's af prime prime or f double prime. Y prime prime. d2y over dy, over dx squared. Or d dx of dy dx. So these two notations are the same, but this sort of combines these as one. So remember, d dx gives you the derivative. So here we have the derivative of the first derivative, dy dx. And a simplified notation is that. We probably won't use these last two notations. When it shows up, I'll probably use one of those two, where we just throw an extra prime on it. But let's look at two examples. Example. Find some higher order derivatives of each function. So A, f of x equals 7. Well, no, let's just do one function. We can combine these as one function. Why not? And I'm going to do it on this board, actually. So, example, find some higher order derivatives of this function. Equals what? 7x to the 5th plus 3 sine x plus 4x. Yeah, let's make it a minus. So find some, that's vague, so I'll just keep finding them until I feel like stopping. And one of the conveniences of the prime notation is you can keep going. You can find the third one and you just throw an extra prime on it. The fourth one you tend to go toward Roman numerals, and we'll see that in this example. These aren't Roman numerals, but writing prime, 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 that's hard to see. But the first derivative, well, we have a power rule here. So we have 35x to the 4. Derivative of sine is cosine. So maybe I shouldn't write sine. Derivative of sine is cosine. Derivative of negative 4x is negative 4. Well, let's keep going. F prime prime of x. Derivative of x to the 4 is 4x cubed. 35 times 4 is 70 times 2, 140. Derivative of cosine is negative sine. Derivative of negative 4, well, negative 4 is a constant, so that derivative is 0. Let's keep going. Third derivative. Derivative of x cubed is 3x squared. 14 times 3 is 42. Derivative of sine is cosine. And the negative carries through. Let's keep going. So here the fourth derivative notation, instead of writing like I, I'm going to put in parentheses I, V, like that for a fourth derivative. These aren't Roman numerals up here, but for convenience, we'll write them like that once we get to the fourth derivative. Fourth derivative, well, derivative of x squared is 2x. 42 times 2 is 84. Derivative of cosine is negative sine. So negative sine times negative 3 is positive 3 sine. Let's keep going. Let's find the fifth derivative. Well, 840 is a constant, so derivative of 840x is 840. Derivative of sine is cosine. So we have positive 3 cosine. Let's do another. Yeah, I guess I'll put it down here. Let's stop at 6. What do I do in my notes? Yeah, in the notes I stopped at 6 also. The sixth derivative, well, 840 is a constant, so its derivative is 0. Derivative of cosine is negative sine. And I'll just say and so on. So you could keep taking these derivatives you want. You'll notice here there is a pattern with the trigs. You start with the function, you take the derivative 4 times of sine, you wind up with itself. And the similar thing happens with cosine. Derivative of cosine, do it 4 times, it winds up being itself. That's a nice observation to make. But these computations are very important. So definitely practice these derivative computations. They all need to become pretty natural, except maybe the inverse cosecant, inverse secant.